All right, so looking at modeling with polynomials. So again, this idea of modeling is that I want to get the best fit to the data as I possibly can. So we use some different modeling tools. So you can use TI-84 graphing calculators. Desmos is a great tool, and the one that I will be using on here today to help us with trying to fit a line to points. So the first thing that you want to think about is your general shape of the points. So again, they're not going to be connected, but we just want to kind of visually think about what we know about general shapes of functions. So again, quadratics are going to be that parabolic shape. So we should see a very definitive decreasing to increasing or increasing to decreasing shape there. When we take and type into our technology that we're using to model, so the line fitting software, we use that general form ax squared plus bx plus c. For a cubic function, we want to be able to see a very distinct kind of S-shaped graph with some very clear maximum and minimums and different end behaviors. And we would use our general form ax to the third plus bx squared plus cx plus d. And then the last one typically that we would use would be a quartic. Desmos has the functionality to do really any level or degree of polynomial that you would like. You are limited on your graphing calculators with what it will allow you to do. But for a quartic, we're looking kind of for that M or that W shape. Sometimes quartics can kind of look like these U shapes with the bottom kind of flattened. We could also model those with a quartic because, again, we don't have to always see that exact number of local max or mins when we graph a function. And then we would use the same process for the function rule with our coefficients and then our decreasing our decreasing exponents, and as we write out those function rules, making sure we have every term there. So your coefficient of determination for a polynomial is going to be r squared. So for linear functions, we use r, and those residuals, the difference between the points and the line, to help us determine how well that fits that line. When we have these curved shapes, we're going to use r squared again. It's still residual values and just telling us how closely that fits to our graph. So we want to be as close as possible to 1. So the closer the decimal is to 1, the better the fit that is modeling those values on that graph. Desmos will automatically give you your r squared value. It's really nice that it just kind of lines that up for you there in the graphing calculator, but on the TI-84 you have to turn on your diagnostics on your calculator to have that do that for you. So for polynomial regression, you're going to be given x and y values in a table. And so you would want to go to, again, whatever technology you're using to help you graph. So you've, again, best fit, just looking at what shape do I see there. Coefficient of determination, again, is that r squared value that tells us how close it would fit to the values. And then your equation is taking the coefficients that you're given and writing out the function rule that you can then use to make other estimates about other values using that function rule. That's the whole point of modeling, is to get our best guess. So if you went into Desmos, you would hit the plus sign and a table, and you put in your x values and the corresponding y values there, and you should see the calculator plot those points on the graph. So if we're just looking visually at what's happening here, I can see that I should be able to model a line kind of that looks like this on top of those points. To max and min there, we have different end behaviors, so that tells me that what we're dealing here with is a cubic function, something that is x to the third power. So after we've identified what is going to best fit the line, then you're going to go to another line on Desmos. Now you have to be really careful because you do have to have these subscripts. So you notice there it has y sub 1 we use the little tilde symbol there that represents our, we use a tilde symbol there that means approximately. So A, B, C, and D are the coefficients. You do have to make sure you have that subscript on the x values in order for the calculator to finish that calculation. And so then once you're done with that, so you see here that we have r squared equal to 1. So this is a perfect cubic function modeling these points. So our function that we would, again, plug A, B, C, D in there would mean that our function rule that's going to best estimate these points would be x to the third minus 3x squared plus x minus 5 would be the final function rule there. And we know that again because we have a coefficient of determination of 1. So we had an example like this where we were modeling some volume and they asked us to write a function for the volume of that prism. Again, volume of the prism, length times width times height. So it doesn't really matter what order I put these in because it's going to be commutative because it's multiplication. But length times width times height, those are the expressions that are representing the values. So what we would do at that point is we would want to go in and look at our graph and see what the graph looks like, which I have here. So this would be the graph of that cubic function. So once we graph that, we would find the maximum volume. So we're looking for the peak that is right here on that graph. And again, the nice thing about Desmos is I just click on that and it will show me what that is. So the maximum volume is the output there. So the maximum volume of that prism that we are given is going to be about 8.209. Because it's, again, the function is representing volume, so that's the output. The value of the width would be 1.786, so that's what the x value is representing. Domain in the context of the problem, we can't have negative volume, we can't have negative width, so the domain is actually going to be only here in the first quadrant, from 0 to about 3. If I had anything more than 3, because I had that part of the function rule that was 3 minus x, then I would cut more of the box away than I had. So I can't take away more than 3 from 3 and still be within the context of this problem. So x has to be greater than 0 but less than 3. And then the range, again, I don't want negative volume, so my range is going to be greater than 0. But if the highest point is 8.209, that would be the high end of the range. So that one's pretty easy and straightforward just because they do give you the equations that you need for that. I don't have to write anything like I would have to for this next example. So Dixie Packaging Company is contracted to make boxes with a volume of approximately 484 cubic inches. Squares are to be cut from the corners of a 20 by 25 inch piece of cardboard and the flaps folded up to make an open box. What size squares should be cut from the cardboard? So we're making a picture very similar to what we just saw on the last screen. And that's actually what the graph is going to look like. I'm going to put that up there. So when we start this problem, we're going to start with a box. We have to cut away squares out of the corners. And then these entire sides are going to have the dimensions of that piece of cardboard, so 20 and 25. So if I think about visually cutting the corners away and then folding that box up, the box is going to be however big I make these squares. So that's what causes that volume to change. So length times width times height. Again, if I had that box, see if I can sketch that box. It's not great, but this would be x this would be 20, take away 2 of those corners, and then I would also have 25, take away 2 of those corners. So my function rule is f of x is equal to length times width times the height. And that's what I graphed in Desmos here. The other thing that I had to graph in Desmos was y equals 484. And the reason that I had to do this is because they're not asking me to maximize the volume of the box. They're asking me to reach a certain point. So that's this green line here, is the value or the volume that we're trying to hit. And so then we can just click on the points where they intersect. Again, I'm only worried about numbers that are going to make sense in the context of this problem. So we have a point of intersection over here at 14, but if I were to cut away corners that were 14 inches, 14 plus 14 is 28. That's more than 25. So this one is not going to work. So we actually have 2 different options here. We could make the sides of the box be 1.22 or 6.87. Part of this is some of the decision making that people have to do at companies when they think about how, what makes sense for the sizing of their companies. Basically, what is it that I'm trying to package and what would be better for whatever object is going to go in that box. So we could say, if it was something that was not real tall, we could let those side lengths be 1.22 inches, or we could let them be 6.871 inches. Again, both of those will give us the required volume of 484 cubic inches.